So today we're going to tackle the periodic table. But forget just memorizing a chart. No. We're going to look at it for what it really is, a map, a super powerful guide that shows you exactly how all the elements work. And honestly, it's one of the most important tools you'll ever use in science and engineering. And hey, if you're an engineering student staring down that BT-101 exam, I get it. This chart can feel like a total nightmare. You're hit with questions about trends and properties, and it is so easy to feel lost. But you know what? That feeling of being completely lost, it ends right now. Because over the next 5 minutes, we're going to completely flip how you see this thing. We're going to turn this confusing chart into a totally logical, predictable map that's not only going to help you get the concepts, but will show you exactly how to nail those actual exam questions. Okay, so every good map has different regions, right? Well, the periodic table is exactly the same. Let's start by exploring its 4 main neighborhoods, or what chemists call blocks. Understanding these is really the first step to being able to navigate the whole table like a pro. So here's the layout. Way over on the far left, you've got the S block. On the right, the P block. Smack in the middle is the D block. And then those 2 rows floating at the bottom, that's the F block. Now this setup isn't random at all. It's all about where an atom's outermost electrons live. You know, the ones that do all the work in chemical reactions. And that location, that address, dictates their entire personality. Let's kick things off with the S block on the left. These are your alkali and alkaline earth metals. Just think shiny, silvery, and super reactive because they are just dying to give away their outer electrons. And you know what? They have a surprisingly flashy side. These elements are the absolute superstars of fireworks. That brilliant purple you see in the sky, that's potassium. That stunning red, all thanks to strontium, both from the S block. All right, let's hop across the table to the P block. This neighborhood is without a doubt the most diverse place on the map. It's the only one that has a wild mix of metals, nonmetals, and metalloids. Those are the elements that can't make up their minds. It's also where you'll find the super reactive halogens and the very stable, very chill noble gases. And here's the key trend to remember. As you stroll from left to right across this block, the elements get less and less metallic. And finally, we've got the middle and bottom sections, the D and F blocks. These are your transition metals. Now, they're a little more complex. Their whole secret is that they have these partially filled electron orbitals, which gives them this incredible flexibility to form all sorts of beautiful colored compounds and bond in a bunch of different ways. That's what makes them so crazy useful in all kinds of industries. Okay, so we've got the neighborhoods down, but how do you actually get around? Every map needs rules, a legend, a key, a compass. For our periodic table map, these rules are called periodic trends. Once we master these, you'll be able to predict how pretty much any element is going to behave. First rule on the list, atomic radius. To put it simply, this is just the size of the atom. Think of it like the distance from the very center of the city, the nucleus, all the way out to its most distant suburbs where the last electrons are hanging out. Okay, now here's where the trend gets a little weird, but it makes perfect sense once you think about it. As you go down a group, atoms get bigger. That makes sense, right? You're adding new layers, new shells. But as you move across a period from left to right, the atoms actually get smaller. So why? It's because you're also adding more protons to the nucleus, which beefs up its positive charge and pulls all of those electrons in just a little bit tighter. Next up is ionization energy. You can basically think of this as the difficulty level for swiping an electron from an atom. The higher the ionization energy, the harder that atom is going to fight to hold on to its electrons. And here is a massive shortcut for your exam. You ready? The trend for ionization energy is the exact opposite of the trend for atomic radius. It's an inverse relationship. As atoms get smaller going across a period, their electrons are held tighter, right? So it takes more energy to rip one away. As they get bigger going down a group, that outer electron is way out there, making it much easier to pluck off. Seriously, just remember one trend and you automatically know the other. All right, our third rule is electronegativity. If ionization energy is all about keeping your own electrons, electronegativity is all about attracting new ones. I like to think of it as an atom's greediness for electrons when it's trying to bond with another atom. How badly does it want more? And guess what? The pattern holds. The trend for electronegativity is pretty much the same as it is for ionization energy. It increases as you go across and decreases as you go down. But there is one major exception you got to remember. The noble gases over in group 18. They already have a full house of outer electrons, so they're not greedy at all. They're happy as they are and generally don't even have electronegativity values. So what's the one master key that unlocks all of these rules? It all comes down to this one concept: effective nuclear charge, or ZEF for short. This is the net positive pull that an outer electron actually feels from the nucleus. Think of it like this. The protons in the center are pulling hard, but all the inner electrons create a kind of shield that weakens that pull. The final strength of that pull is the real reason behind every single trend we've just talked about. Okay, so we've explored the map, and we've learned the rules of the road. Now it's time to put it all into practice. This is where the rubber meets the road for your BT-101 exam. We are going to use what we've learned to solve an actual question from a previous year's paper. Let's do this.
And here it is, pulled straight from the December 2023 exam. Question 7 asks us to write the trends for ionic size, electronegativity, and electroaffinity in a group and in a period, giving suitable reasons. Okay, let's break this thing down piece by piece.
So the first part of the question is all about ionic size. And remember, an ion is just an atom that's either gained or lost an electron. So the real question is, how does that change its size compared to the original neutral atom? Here's your answer. A positive ion, a cation, is always going to be smaller than its parent atom. Why? Because it lost an electron. So now the nucleus can pull the remaining electrons in even tighter. On the flip side, a negative ion, an anion, is always larger. That's because the extra electron it gained repels the other electrons, forcing the whole electron cloud to puff out and expand. That is the exact reasoning you need for the exam. Now for the last two parts of the question, electronegativity and electron affinity. And just a quick refresher, electron affinity is the energy change when an atom gains an electron. And would you look at that? They both follow the exact same trend. They both increase as you go across a period and decrease as you go down a group. And the reason? It's the same logic we've been using. A stronger net pull from the nucleus, that higher effective nuclear charge, makes it easier to attract an electron. Simple as that. We have covered the layout, we've covered the rules, and we've walked through a real exam question. Now, to make absolutely sure all of this sticks when you walk into that exam, I want to give you one last thing. Think of this as the ultimate key to our entire map. And here it is, your ultimate cheat sheet. Just look at the pattern. Atomic radius is the odd one out. It's the rebel. The other three, ionization energy, electronegativity, and electron affinity, they all follow the same trend. They all increase to the right and decrease going down. So if you can just remember the trend for atomic size, you can figure out all the rest just by flipping it. This is your secret weapon for that last-minute revision. So you see, the periodic table is so much more than just a chart for your chemistry exam. It is a predictive powerhouse. It's a map that lets you, as future engineers, understand and actually predict the properties of any material you could ever want to work with. You now hold the key to that map. So the only real question left is, what are you going to build with it?